go up?
Sure. Unfortunately, unlike a lot of other times, I don't understand too much about what he's talking about. Um, I mean, it seems to be a post about like if what if there was I guess a programming model, like a programming language or something that allowed you to write code that was designed to be run on a like a pure distributed system in some sort of native way. I have a hard time envisioning what that actually means in practice. Like, each distributed, computer will be running of like this like this language, so almost like a node that would be just sort of like a general way, and then it would receive the code from somewhere or be running it. But he seems to be against the idea of, oh yeah, you're writing for a particular machine. So I'm guessing the parts that go on the individual machines are some sort of general thing, and then it tries to then you write the code over this sort of background of general nodes that are sort of hidden. But then he goes against the idea that yeah, this shouldn't be so opaque. I don't know. I have a hard time understanding what he's talking about. So uh, I mean, so it sounds like a good idea, or I'm sorry that happened. I guess I'll move it up. Joan Raj.
Yeah, I'll talk later. I was fixing some audio issues. Passing on to Anant.
Yeah. So first, I mean, the article seems to indicate that the distributed systems programming in general has stalled. I thought it might be about sort of the big issues or like a big list of audit of issues with the current uh, paradigm, which I thought was quite there. But it did bring up sort of, for my own understanding, I found myself remembering some of the earlier readings we've done. A couple of articles that struck at me was one, The Big Ball of Mud, that we had read earlier. And the reason I remembered that was, if I remember correctly, compared like different sort of architectures, like shanty towns and the Big Ball of Mud itself, and sort of I think sharing layers and so on and so forth. But what I remember from that article and why it reminded me of reading this article, reminded me of that was it seems like the distributed systems in general is like no single recipe for how to do this. It seems like it's entirely application dependent, and how you design a distributed systems is to me at least seems like the application that needs to be served. So how you collocate information, or how you sort of even uh, like distribute compute or do the synchronization is all dependent on the application. So that was the sort of the primary thread that I kind of went on. The other thing I did was I was trying to talk to LLM about the sort of I try to go to the basics in terms of what are the primitive units of logic and computing, and how does that scale into distributed systems. And I thought it was sort of useful, at least for me, to orient myself around that, and that the sort of the basic transistors get grouped into a bunch of logic gates, and you have only like 7 or 8 different logic gates, which then combines into these sort of higher level objects into like lattice, register, and so on and so forth. So at the individual machine level, that's kind of how a machine works in some sense. And if you compare that to like a distributed systems, you have the sort of same sort of orchestration, but except there are other challenges that comes in, especially in timing. I thought that was interesting. The communication latency that comes as a result of having different machines. Uh, and sort of the third one was the sort of consistency models, which again relates to the CAD theorem, which becomes important in distributed systems. I thought none of that was sort of directly addressed in the article. I thought that have been nice to get some insights on. The other thing I did was, I mean, I was thinking about, since we were reading on the other track on the Ethereum protocol, I was trying to think of like what are the sort of uh, uh, what are the advantages or what are the things that the EVM would solve for, and what are its sort of shortcomings in thinking of distributed systems. And it seemed to me that EVM has like some sort of fundamental instruction set and execution model, and built in as a result of fault tolerance, like Byzantine fault tolerance, it's got this built-in consensus that seems to work. Would have been nice to sort of get a sense of uh, blockchain-based compute systems, how that fits into their sort of, and the programming language that you kind of have on top of that, how that fits into this model that this article talks about, or at least the shortcomings that the article gets at. The other article that I was reminded of was the sort of, because of the LLM section in the article, uh, I think there was an article we read something along the lines of, let me find it. Uh, it was like an applied LLMs article. I'll share it. It was a big article on like what are the sort of issues that they had learned building on LLMs for over a year, I believe, at the point. And yeah, I mean that article was getting in more in details about the sort of issues with building with LLMs in general. The one thing that I did find myself questioning and think about was the article gets at, or at least says that the LLMs are not particularly good at correctness, and uh, and that it's sort of becomes even harder to distribute them across different machines. But that kind of seems to me like it's a feature, not a bug of LLMs, and that maybe the modern applications will have to build around that or with it. But anyway, I will stop there. I will pass it to Venkat.
Yeah. So I was relying on ChatGPT a little to understand the article. The two main criticisms it made, which I agree with, is one is the author is ignoring the few theoretical, conceptual things that we know about, like the CAP theorem. So it was kind of interesting to try and apply the CAP theorem lens to the three approaches he mentions. And ChatGPT did, I think, an okay job. For example, the first approach of externalizing distribution, it gives you high availability. Let me hold on, just pull up what it said. The first one, external distribution, gives you strong consistency, but availability is often sacrificed, which kind of makes sense if you're relying on external thing. Like when you get it, you don't have to think about distributed programming problems yourself. But yeah, Amazon or wherever you're getting it from can just go offline. So it's kind of like a user level version of the CAP theorem effect. So the implication of that is these are not like stagnation or other like technical cultural effects. They're artifacts of CAP theorem. So it's not that distributed programming is stalled. It's because of fundamental limits like the CAP theorem, we are where we are. So that's one response. The other response was there's a lot more tooling that the guy doesn't talk about. So I didn't recognize most of what it was talking about. But there is like apparently like huge universes of tooling for whichever regime you want to optimize for, and it ends up being a practical matter of like the specific constraints of the application you're solving for. So my takeaway from that is, yes, these may be three different basic programming paradigms, but really the way people solve these problems is to start with the distributed application, understand the constraints and the CAP theorem regime they're operating in, then pick an approach that optimizes for that regime, and then use a lot more tooling than this guy seems to. So the programming piece is just one piece of the puzzle, right? How you program, whether you use Rust or C++ or whatever, that's just one piece of the puzzle. There's lots of other pieces. For example, like, are you using any observability and monitoring tooling for fault tolerance, right? So that's typically not considered as part of the programming model. Or what kinds of like large scale orchestration technologies you're using, like Kubernetes or containers. So that's, I think, a reasonable point they're making. LLM's angle, that's kind of interesting, and though not in the way the article talks about. The interesting angle on LLMs here is the underlying low-level kernel level of actually making LLMs work, both as in training and inference. The lowest level problems, like a couple of levels below PyTorch, they are in fact examples of distributed computing problems, and they are exactly as hard as this article makes out. Like if you're like doing a really big matrix multiplication that scales across multiple AI accelerator cards, across PCI Express connections or Ethernet connections at like a rack scale or even a data center scale, you're solving like a multi-level data movement problem where like a single big but apparently simple problem like multiplying two very large matrices, it's being broken down into lots of little pieces, and bits of data have to fly around through multiple levels of caching, and nobody has solved this problem well. And it's not really a question of like programming methodologies. It's more like the underlying math itself is like annoyingly difficult, right? Like if you ever actually manually tried to multiply two matrices in sort of a decomposed way, you would have seen that, right? Like sometimes it's very easy and it looks as simple as MapReduce, where things separate easily. Like, multiplying two diagonal matrices is very easy because you just do 1, 1 of one matrix multiplied with 1, 1 of another matrix, and 2, 2 with 2, 2. So it's like completely decoupled. So I'm making up a trivial example, but to use a MapReduce approach for this, if you have like two huge million by million diagonal matrices that you're trying to multiply, all you need to do is take each pairwise diagonal pair of elements and give them to one processor, and each will solve that computation, and then you can just assemble it into one large million by million diagonal matrix. So that's a very trivial example of how it can be easy. But if it's a full and non-sparse matrix, you'll end up with the result of one small computation in one processor then has to go up through several levels of memory hierarchy across boards, across servers. You don't know what the latencies will be like. So it's hard to look at that problem from this particular lens this guy is talking about. That's about programming paradigms, because there it seems like all the difficulty is not in how clever you are with programming paradigms, but the fact that the matrix multiplication problem itself is like it's a distributed computing problem that doesn't lend itself to very easy breakdown and tearing apart. It does not have a natural decomposition structure. So I guess what I'm trying to say here is the difficulty of how hard a distributed computing problem is not really a function of like how clever your programming paradigm is, but actually how distributed the problem itself is. Is it decomposable or not? Can you do MapReduce or not? Is it like full rank with like lots of complexity in the basic operations like mapmult? So yeah, but this is kind of a little bit thought-provoking. And I want to mention like my own extremely limited sort of like pseudo distributed programming experience was actually not in a distributed programming environment at all, but this was way long ago when I was doing some simulation programs of basically multi-agent robot systems. So imagine multiple robots wandering around a map. Each is making its own navigation decisions, and then you have like the global state update, and they have to interact with each other. So I didn't know anything about distributed programming, and I didn't want to learn a distributed programming approach just for that research problem. So I basically faked it in MATLAB, which is a regular sequential programming language. And the way I did it was basically very fast stepping and switching. So each of the robots would be kind of like a thread of its own computation. It would do a step of its navigation, maybe move one step, and then you do the same with the other robots, and you do this repeatedly. So you'd basically simulate like multiple parallel threads in sequence, and then when they actually ran into each other, or you have to do some interaction or obstacle avoidance, you would do some hacky way of like using semaphores or like shared files on the disk to exchange state information. So it was sort of like fake distributed programming, because these were like the maps were in fact very large matrices and were too large for the computers I had at that time. This was like 2003. And I did get a sense of why these problems are hard and what you can do. And I got the sense kind of similar to like, NP complete problems, or it's like there's no systematic way to solve them. So just as when you're solving an NP complete problem like traveling salesman, what you do is find like a regime that you kind of have good intuitions for and find heuristics to work with them. It's kind of similar with distributed programming, is my sense. It's like you get a sense of the problem and then solve it with heuristics. So in this case, it was distributed robotics, and I had some idea of good heuristics. So I effectively kind of solved it without learning any distributed programming. Anyway, sorry, that was like a long random riff. Over to Nathan.
I I am not sure I actually have anything to add that Venkat hasn't already said in fewer words than I wrote. I think I had a lot of the same reactions, but from a more theoretical point of view. I mean, that said, I'm not an expert in this. Like, my interaction with the sort of programming that's big now ended more than 10 years ago, and I haven't used that math in a long time. So I don't have that much there, but I do think I'm going to just echo. I'm still going to talk because why not? I'm going to echo. I think what a lot of what Venkat's saying is I think a lot of that the complexity the author is complaining about is a reflection of trade-offs that are necessary to deal with fundamental constraints of the underlying model. And I think that the fundamental constraints actually sort of emerge, and I think Anand hit on this a little bit, from the nature of computing itself, that all of our computers are finite precision state machines, which means that they operate over, we could say, they operate over these big spaces, but fundamentally they're just operating over ALF naught. So they like sort of a discrete, infinite discrete space at best. And so the fact that it's like at some point I run into a constraint and I have to essentially linearize what's happening, or that I'm complaining that at some point, linearization is biting me, like, is just sort of the nature of that beast. And I think it's notable that you see a lot of these same problems with coordination and communication in biologic systems, which, while they have a lot more freedom of movement, have some similar constraints in the sense of like time happens at the, this is going to be, maybe Venkat will disagree with me, but like time at the most fundamental level is this like linear sequential thing. And like, at a high level, maybe we disagree with things, but like when the protein is moving through the cell, like the thing happens and the thing happens and the thing happens. And that's a very similar, not exactly the same, but a similar set of constraints. So it's not surprising to me that similar problems and similar solutions emerge. So from that perspective, I kind of feel like what the author wants is not so much a new programming paradigm, because what you have now is a number of paradigms, and they're each kind of like specialized in a little bit. They're like, well, if I have a problem and it's amenable to these particular constraints are not issues for me, then it's really easy to do it this way. And if a different set of constraints are non-binding, then I can do it this way. And so the very classic, you just, depending on what constraints are non-binding, and what constraints are binding, you're going to choose different approaches that are going to be more or less effective to solve that problem. So it feels like you can't do a lot with programming paradigms. Like eventually the paradigm has to reflect at some level, no matter what the abstraction, the underlying reality of the situation, the underlying reality that these are finite precision state machines, that they're just step by step by step by step, and that there's not infinite degrees of freedom for these things. And so it feels like what the author wants is a new programming hardware. Like it feels like this would be a more valid question if we were saying, what does a programming paradigm look like for quantum computers that are doing computations non-locally and are, when you are merging and unmerging states are not subject, at least, I shouldn't say, this is an interesting theoretical question, whether quantum computers are subject to precision, but may not be subject to precision in quite the same way. At the very least, that the system, the sort of macroscopic, more classical systems that we're familiar with are subject to. And so it feels like if you had a system like that, then you would naturally have probably other programming primitives, because you couldn't work with things. Some of these the linear sequential things that you actually have to work around would almost be the hard part that you have to work towards in some aspects of those systems. So I feel like there's I think I agree that there's a little bit of the author just not being mindful of the underlying constraints the system is in, and that whatever level you're at some point your programming paradigm has to reflect the underlying nature of what you're programming over. So yeah, those are my thoughts. If there's time, I have a funny story that this art reminded me of, but I don't want to speak too long, so I'll pass up to Anurag for now.
Yeah, so I quickly went through like the author doesn't seem to go through all the different. For example, this reminded me of the programming language Erlang, and Erlang seems to touch some of the things the author wants. So, and like you don't have to actually be trying to build a distributed system. Some of the problems you will already face when you are doing multi-threaded programming, and like I think Venkat mentioned, it's trying to simulate a multi-robot system with multi-threaded system. So, like some of these problems are, you will already see that. And and I think like the programming languages itself are sequential because we think in sequential ways, and then like kind of uh, we try to implement that in hardware, how it's done in a distributed way. But like when you are programming something, you think sequentially, and then basically like you build upon it. And I think that is what kind of Erlang does. And then there are like some parts which allow you to build a distributed fault tolerant system in that. And yeah, the article did not touch all those programming languages. So it seemed to me that the uh, author basically wants a programming language which addresses these problems. Yeah, those were my quick thoughts. Open floor, I guess.
I guess if we're an open floor already, I'll tell my story. So as I was reading this, I am reminded of a friend of mine who many years ago has their daughter's a toddler and takes their daughter to a park. And the daughter wants to get on the swing set, and so get on the swing and start pushing. And the daughter's like, no, I want to be on the other swing. So my friend takes their daughter off the swing, puts the other swing, starts pushing. No, I want to be on the other. And then it just escalates, and it just escalates and escalates, and my friend's switching swings and pushing. Nothing makes it better. And then suddenly, my friend realizes that my daughter wants to be on both swings, and this is just a really hard lesson in life that you just can't be on both swings. And it just this sort of like article put me in mind, because it really did feel like, from that constraint perspective, it's like you really want to be on both swings here, but you just can't be on both swings. You just can't have the system that gives you everything. So that was the one that I left out.
I'll jump in just for two reasons, real quick. I have been hearing Notebook LLM is good for studying stuff, and I can feel with today's test, like, yeah, I bet it is. The built-in affordances for things like over on the right in the screenshot, the bottom right that I did. Plus, I haven't tried it because there wasn't time. But I bet the generated podcast, I think people are calling them, in the upper right of that screenshot probably is interesting. But the other thing that's on my mind is, I forget if it came up here or in a gov call, but we were talking about, the ability of a human, any average human, to grok big, complicated things. And I think I had said something like, yeah, that's kind of fixed. And Venkat, I think you had said, oh, it's not at all fixed. And then right after that, I started reading, I dropped the screenshot in. Ken Kaufman is a modern bird savant, and he did this whole book about the birds that Audubon missed. So a deep dive on Audubon himself, and how, in spite of the fact that Audubon was deeply a bird guy, he could only see the things that he could see at that time. And what now these bird nerds can see about birds is just phenomenal, phenomenally further along. And so even though my brain I barely even know what this guy's talking about, right? But it was reassuring that at least I'm not the only, it's tough for everybody. But also the humans will be able to follow this stuff more and more. I get it. That's cool. And then my last question that I asked the Notebook LM was, well, like, what will this actually look like? My brain always is happier when I can see what it looks like in reality. And it gave me a pretty big punt question. So if you look at if you click through on the link, and if it lets you see it, you can at least see what Notebook LLM said about that. What will this actually look like in the real world? So I'll pass back to the group after those 2 points.
I'm thinking more about the idea that the solution space is a function of like the structure of the problem, and how that's kind of like a relaxation of what looked like really harsh constraints, like the CAP theorem, right? So there's lots of theory about this. One that I remember from grad school is that the general distributed control problem, like say you have a swarm of UAVs flying around and you want to control them in some formation, if you pose it as a general mathematical problem, you'll end up with the conclusion that due to theorem A, B, or C, it's an impossible problem. But that's because you're trying to solve it generally, and we already talked about like how usually you do heuristics, but you can get more systematic than that. So this is one of the results my postdoc advisor came up with. It was something like, if the controller structure mimics the problem structure formally, you can solve the problem. The constraints go away. So in this case, it's something like, if there's a matrix representing the positions of the UAVs in some sense, and your control architecture, which is like which UAV is talking to which other UAV. So your communication graph across those UAVs, if they match kind of the physical layout, the system becomes controllable. And this intuitively makes sense, right? Like, to take the simplest case, if you have a line of cars going down the highway and you want to control them, and they're like, driverless cars, and they're driving very fast and very close to each other, like, at speeds and separations humans couldn't drive. So this was an early problem being solved in the late 90s. So bumper to bumper, 80 mile per hour strings of cars. And if you pose this problem in a general sense, you'll discover that it's like, impossible to solve. You can't stabilize this, it'll crash, things like that. But because you actually have like a simple geometric structure, if you make up like a simple control architecture, in this case, what they discovered was if every car just knows where the next car in front of it is, so the distance to the car immediately ahead, plus the position of the lead car, you can get stability. So there's famous result in what's known as string stability. So that gives you an idea of like how these things work, which is look at the problem, look at the structure of the problem, and actually put solution elements in that mimic the structure of the problem itself. So put your communication channels in specific places, and then you end up with like a solvable problem. And I'm not sure how to generalize this point, but I think the basic idea is that, we'll put it, in practice, the theoretically very hard problems don't actually show up very commonly. And this has been a repeated result in research. Like back when computational complexity, so P versus NP stuff, was like a big research topic, there was a period when people were actually struggling to find actually hard instances of the complex problems. So take problems like, the traveling salesman or Hamilton circuit. So these are problems you can state very simply. So traveling salesman is find a route that visits all cities, right? But it turned out that if you just search the space, it's really hard to find actually hard instances of the traveling salesman problem. Like usually you look at the problem, you can say, oh, this clearly belongs in this regime, and this heuristic works pretty well. So it turns out that all the hard instances of such like theoretically hard problems, they're clustered in a very narrow region of phase space. So phase space, like, the freezing of ice has like a phase transition from liquid to solid, and there's like a narrow range between around 0 degrees where you have like neither liquid nor solid state. So something like that is what they mean by phase transition. Like in the problem phase space, there's a very narrow range where you have to find the actually hard problems. I think something similar might be true of distributed computing. Like the actually hard distributed computing problems are actually hard to find and rare. Like Nathan, your anecdote about your daughter wanting to be on 2 swings at once, that's like a literally impossible one. You weaken that a little bit, and you might get like, really hard problems of like playing with swings. So I'm not quite sure how to think about this, but I suspect in practice, all problems we encounter will not fall in the difficult regimes of distributed systems, and we will actually be able to solve them. But sometimes they will. And I think that's one reason cryptography is interesting, because cryptography relies on the existence of problems that are actually hard in the typical case in at least one direction, right? So the typical traveling salesman problem may not be hard, but the typical factorizing a prime number problem is hard. It's not like you can look at a very large number and say, hey, this happens to fall in the one of the easy classes of prime number factorization. So yeah, there's something going on about that. Sorry, that was another longish riff. So
yeah, I think there's. Oh, sorry, Ben.
Well, no, I was just going to say that this is something I've also noticed about, just a general. There are a lot of problems that are basically impossible to solve generally theoretically, but if you actually look at a real instance and try to chew on the actual details of whatever you're actually dealing with, you can come up with like, if not a general solution, a good enough solution that works well enough. So if you fall out of the abstraction and just actually work on the problem, you find that, all right, this is actually doable with a little work.
Yeah, I was going to kind of say something similar from a more general point of view. When I was doing my grad program, like one of the things we talked about in the math department a lot, the applied math department, was that when you were modeling, it was really important to understand the limits to your model. And it's something that I think that a lot of people subtly forget. Like, you know, I don't know, my first thing is like, everybody knows that like when the temperature gets really high, things break down, but maybe not everybody knows that. But like, you know, I think most people, like, they've heard enough by adulthood. They're like, oh yeah, if I was traveling near the speed of light, things would get wacky, or something. So they kind of know this at like a gross level, but I feel like we are oftentimes not good about recognizing model boundaries that are maybe hidden behind a couple layers. And I think that's maybe a different way to formulate what's wrong with this particular essay, is that all of what we're doing with computers is essentially modeling problems. So even if it's not simulation, like even if it's like, you know, distributed ledger or whatever, you can think of this the same way. There are bounds. We've made a set of assumptions. We've built a set of systems. There are bounds here. And a lot of times what's happening with programming paradigms or programming languages or frameworks or whatever is you're kind of trying to hide those bounds, because oftentimes things will break when you go past the bounds, but also sometimes things get weird even as you approach those boundaries. So we try to hide those, but then I think people start to forget that those boundaries do exist, and you have to be aware of the region your system is valid in. And I think that kind of comes to, like, you know, where Venkat's coming from is, you know, those hard problems. A lot of times what happens is the reason you can get these models that are very work is you're like, well, how can I shave off that hard part of the solution space without and retain the majority, the largest possible chunk of the rest of the space? And then I can make a model that works within that and is really, really good. And that's a lot of what we do. And that's a really important thing that we don't tend to realize, and we tend to forget that it is sort of all models all the way down there, and trying to avoid these difficult bits. And I think Venkat's right. It's like cryptography is also really cool because, you know, it is, I think, one of the few places actually where we have learned to harness hardness. Like, there is a bit of a like Promethean nature to cryptography, in that we spend most of computation, most of our thinking, trying to avoid intractable problems, and yet in this one area we have harnessed this destructive logical force of impossibility to the ends of creating something constructive. So I do think there is something kind of cool and Promethean and very different conceptually, philosophically, with cryptography than most of the rest of mathematics and computation. Yeah, that was rambling. Oh, one correction, just so nobody. It was a friend's daughter. It wasn't my daughter.
I forgot the detail. One last quick point in response to something Ben said about good enough and approximate solutions. That one's actually a very fragile assumption. So the point I was making was there are easy regimes of problems and hard regimes of problems, but that's not the same things as approximate versus exact solutions. And in fact, one of the sort of like mindfuck moments for me in grad school was learning that there are NP-complete problems for which the approximation problems are also NP-complete. By which I mean, even the problem of finding good enough solutions is intractable. And one example of that is actually very familiar, which is that the Hamilton circuit problem is in fact the approximation problem of the traveling salesman problem. So for those of you who don't know, the traveling salesman is well known. It's you're given a set of cities and you want to find the shortest route that visits all of them, right? That's the traveling salesman problem. The Hamilton circuit problem is given a set of cities and a set of roads connecting them, you have to answer yes or no to the question, does any road exists or any path exists that visits all of them. There's another one called the Chinese postman problem that's the dual of this. But the point is, this is also an impossible or intractable problem in the NP complete sense, which means if you want to find approximate solutions to the traveling salesman problem in the general case, that's also intractable. So this is, I think, an interesting point that often good enough is also not within reach. But yeah, easy and hard tend to be separated in problem space. Anyway, we are at 9, so we'll be back next week with the second episode of the EPF readings, which Anuraj will lead. So, see you guys next week.